Why is the world of quantum physics so weird and bizarre? Why is that our common sense seems to defy the logic of quantum world? What could be the reasons? What are some of the fundamental concepts of quantum physics that we know but we have misconceptions? Well, quantum physics is peerless at explaining reality but assaults our very own intuition of how reality should be. It seems like the fault lies within our intuitions. Well, in this video we are going to take a complete tour in understanding the reason of this strange behavior as well as the fundamental concepts of quantum physics in a very detailed manner. We are going to overcome some of the misconceptions caused and understand the most fundamental and important concepts in an easy manner, keeping the mathematics to the minimal. However, I would request the viewers not to skip any part of this video as it is going to be super interesting and very important in your learning. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this fresh video, ABC of Quantum Mechanics. First, let us quickly look into what are the topics that we are covering. First, we will understand why I am making this video, the basic objective, what is quanta and quantization, the birth of quantum mechanics. We would clear the misconception that we have. We will also look into the basic misconception, what is the difference between classical and quantum physics. We will look into photoelectric effect, Bohr's atomic model, de Broglie's hypothesis, wave-particle duality, and clear some of the misconceptions of quantum superposition. We will look into quantum entanglement and clear the misconceptions regarding uncertainty principle and quantum tunneling. Finally, we will put all our knowledge into use, that is a practical usage, and understand what is quantum computing. Before we go ahead and start this video, I would request not to skip this because all these concepts are related with each and everybody. One concept is related to another. Well, these being the topics covered, first let us understand that what is the basic objective. I mean to say why I am making this video. You see that I would like to give you a complete and comprehensive idea of what goes around the world of quantum mechanics. I would like to remove the misconceptions, and yes, there are misconceptions which you will see in the video. I would like to give you an in-depth understanding on the principles of quantum mechanics and tell you the real difference between classical and quantum physics. I would also like to tell you what is going around the current developments and advancement in the world of quantum physics, and finally let you know the core fundamental concepts of quantum physics. So these are the objectives to summarize, to give you a complete, comprehensive, clear idea and understand the real difference and remove the misconceptions which persist in the understanding of quantum physics and give you a core fundamental idea. So being this the objective, the first question that comes in our mind while starting quantum mechanics is that what is the meaning of the word quanta? And that would be, we would be dealing in this part of our video. Well, if you see, the Latin word is basically, the word comes from quantum or Latin quanta. It generally means a kind of a so much or as much. I mean to say a specific quantity, and quanta is basically the plural. So we can say the minimum amount of any physical entity involved in an interaction. It is often used in physics as a measure of the smallest amount of something, and it is a fundamental notion that physical property can be quantized. Now, what do we mean by quantized? We will soon look into up, but this is basically the idea that the minimum amount of physical quantity, and it is used to measure the smallest amount of something, and a fundamental notion that physical property can be quantized. Now, the question is that this is basically called the hypothesis of quantization. Now, what do I mean by physical property to be quantized? Coming up in this part, next part of our video. So before we go ahead, you see, it is a procedure for constructing quantum mechanics from classical mechanics. This is a kind of a more scientific definition. But first we will look into what do we mean by quanta, coming up in the next part of our video. Well, quantization is something that we called something which is very discrete. These things, as you can see, that these green dots are basically discrete chunks. That means these are quanta, this can be seen, and these are very discrete. Similarly, when we talk of the atomic model, you will see that the atoms and those electrons going around the nucleus, they have a specific orbit, 1J, 4J, etc. And that is the reason that in general in classical physics we see things to be very continuous, and in quantum mechanics we see that things are to be quantized. That means from continuous movement we move into something which is discrete. So energy allowed of a particle have a value in energy, and only certain values of energy are allowed. That means we are not in a continuous flow of things, but something which has to be discrete, something which has to be quantized. And as you can see that it tells that only certain values of energy are allowed, not all values. That is basically the idea of quantization. Now, these are all examples, but can we take an example on our daily life and see what is quantization? Let us see into the next part of our video, where I have taken a simple glass of water, and if I ask you how much water would go in this cup, your answer would be any amount less than something. Or you can say that these are composed of H2O molecules, and this is a 250 milliliter of water, and using Avogadro's number you can calculate this number of molecules of water. So you can actually count the number of molecules, 1, 2 and so on. So the amount of water in the cup is to be quantized. Now why it is to be quantized? Because we really want to know, and with science we can calculate an average amount of molecules over there. Now we cannot split the molecule obviously into two halves, right? This and this. So it only appears in discrete value, that is the quantum of water is one molecule. So the quantum of water is basically one molecule, and here it tells that quantum mechanics tells us that we can only transfer these things in discrete pieces. So this is basically a quick example of what is a quanta, what is quantization. So we are trying to tell that how much water is there in this glass, and that is discrete, that is specified, and that is quantized. Well, if you want to know a little bit more about this quantization part, I've got a video in my playlist, Introduction of Quantum Mechanics Lesson 2, where you can go and you can find out the little bit more about this quantization part. But we are done with what do we mean by quanta. Now the question comes that now that we have understood the word quanta, the question is that how did quantum mechanics took birth, or what was the reason, or what was the event that marked the birthday of quantum mechanics? Well, first of all, I would like to tell you that in general, in relativity theory, the birth of quantum theory was also slow and required many hands. It emerged in the course of the first quarter of the 20th century with many contributions of physicists, including Einstein. Now, you can see that during the early 19th century, chemical research by John Dalton and Amadeo Avogadro lent weight to the atomic theory of matter, an idea that James Clerk Maxwell and Ludwig von Boltzmann were actually others were building upon the establishment of the kinetic theory of gases. The success of kinetic theory gave further credence to the idea that matter is composed of atoms, yet the theory also had shortcomings, and that could be only solved by the development of quantum mechanics. Ludwig Boltzmann in 1877 said that the energy levels of a physical system such as a molecule could be discrete rather than continuous, and Boltzmann's rationale for the presence of discrete energy levels in a molecule such as those of iodine gases has its origin in statistical dynamics. Then we got the development of Max Planck, who in 1900 quantized energy, and what we came to know is what is called the Planck's law. Now, in general, people know this to be the birth of quantum mechanics, starting from Dalton, Avogadro, Boltzmann, Planck, Einstein, Heisenberg, and so on. But what I would like to tell you is that this is one part of the story, but there is another part very interesting, the birth of quantum mechanics. Let us see in the next part of our video. Now, here is a gentleman, Ernest Gaston Joseph Solvay. He was a Belgian chemist, philanthropist, born in Rebec, and he suffered from acute pleurisy. And in 1861, along with his brother, he first formed what is called the Alfred Solvay, or the Solvay Company, which actually produced something called the soda and ammonia, right? So Actually, Ernest Solvay cherished physics most, and he funded Brussels in a series of councils bringing together the era's most brilliant scientists, right? And first was held in 1911. Einstein, Curie, Langevin, Nernst, Planck, Brillat, Lawrence Rutherford, Poincaré, and others. A similar council of chemistry was held in 1922, but this was very important. Why, we will soon see. Now, this is the Hotel Metropole today, where the first Solvay conference was held, and this was in 1920 from a postcard. Now, in a letter of invitation dated 15th of June 1911, Ernst Solvay explained that he conceived the first meeting as an international scientific council to elucidate some current questions of molecular and kinetic theories. Hendrik Anton Lorentz was the chairman of the first Solvay conference, and it was held in Brussels from 30th of October to 3rd of November, and the subject, you see, it's quite obvious: radiation and quanta. And the conference looked at the problems of having two approaches, namely classical physics and quantum physics. Now, I just want to make a note that, as you can see from here, that the birth of quantum mechanics actually took place. This was the formation of the first Solvay conference, and the decisive decision was on radiation and quanta. And you can see here a small conference, about 24 participants. Einstein first made his debut about non-German speaking people, and here you see classical physics and quantum theory was first discussed on the table. Duality of wave and discrete packet was also brought over here. Quantum theory first came up front, and Curie's letter of recommendation, that's a different story. I have already made an interesting video. And Solvay's decision for sponsorship until 2022, we have the Solvay conferences constantly going on. So I think that this should be considered in 1911 as the birth of quantum mechanics, because on the table with such many luminaries, great physicists all around, the quantum physics was discussed, the wave particle duality and the discrete packet of energy that it releases actually was discussed first. So this marks the birth of quantum mechanics. However, if you want to know a little bit about the Solvay conferences, etc., I've already made a very detailed video on how it started, what it is all about, and how these conferences are still going. You can check it out in this my playlist Solvay conferences, which I have given a detail. Now that we have understood the birth of quantum mechanics, the next question that comes to our mind is that here we discussed in 1911 what is classical physics and quantum physics. Can we know what is the actual difference between classical and quantum physics? Let us see into this part of our video. In general, when we talk about classical physics, we means that what is a state of a system. So in physics, we call a state of a system basically is a list of variables that, when it is accurately specified, not only gives an information, but it also gives an entire time evolution. For example, if I've got a system which has got a position and momentum marked as x as position and p as momentum, then if I take something which is on an observable scale, that means we make an experiment which is observed, we get a function q of x and p. So anything observable we find out here. So if we know the particular position and velocity of a particular system, all measurable quantities such as momentum, angular momenta, total energy, etc. can be observed, and this is what is called observables. And this position and momentum in technical terms is called the state of the particle. Now, when we talk of the state of the particle, we understood that we know the position, momentum, the entire history and the time evolution and other observable things are discovered. Now, can we give an example? Let us see in the next part of our video. So the state of a system is something which is called a position and momentum, and the measurement that we do is also a position of momentum. No dilemma, no ambiguity regarding this. Now, we can perform an experiment to determine the state of a system. So we take a two-state system, for example a coin which has got a head and a tail, and we say that if there is one particular system which has just got only head, superficial, and it has got no tail, then the time evolution will be head, head, head and head. That's simple. If we get a tail, it would be tail, tail, and tail. That's quite simple. So what I'm trying to make a point is that the future will depend only on one observation, because we have got only one state of a system, that is either head or a tail. Now coming to the next is that if in a classical system we know a position or momentum of a particular particle, but in case of a quantum physics we get what is called a probability distribution or a probability density, which says that the particle can be here and be here, can be here and can be here. So only we get what is called a probability, and we calculate the probability by this Greek letter psi, which actually shows that the mathematically describes the wave characteristic of a particle. Even if we square it, what we get is a probability density. That means a kind of a likelihood that might be the particle is up there or down there. We can only know the likelihood of the particle, nothing more than that. Now this being said, that let us see what are the differences that we can quickly cite out. The first is that this is where the particles are quantized. That means they have a distinct state as the electrons moving around the orbit. So these are distinct chunks on quanta, but in classical physics we see that continuous position, velocity, etc. they are actually continuous and take any real value or range. It can go up to anything, but quantum physics will only take discrete chunks or quantity. So here it is, quantum physics introduces quantization, where physical content values have a discrete value. We see next that what is called, it has got a deterministic equation like F equals to ma, or the equations of mechanics. But here it is only a wave function, which we will soon discover what it is, and it is guided by this Schrodinger equation. So it again tells the difference between classical and quantum physics. This is deterministic and this one is guided by wave equations. What we also see is that classical physics considers wave-like nature of light, which is a kind of electromagnetic wave, and which is propagating and it is generating electric and magnetic field, whereas here we see what is called a wave particle duality. That means the light has both particle like and wave like properties. Further going forward, what we see is that in classical physics we get a position and momentum of a particular particle, but here it is all well defined. But in this case it is guided by the uncertainty principle, and it tells that more precisely the position of a particle, the less precisely its momentum. However, I would like to rectify, this is not exactly the right way to understand uncertainty principle. We will soon explore the real meaning of uncertainty principle, but this is what the basic difference between classical and quantum. And we also know that in case of classical physics, all those equations that we see, more or less they takes place on a real plane or real number, and these things all take place in a complex plane, and you can see the square root of I, that is the imaginary number, is everywhere. Well, I would like to say that this is actually not everything. However, I have made a very detailed video on the further understanding of the difference between classical and quantum physics, and this is the one which is there in my playlist. You can just go and check. However, this gives a kind of an idea, a real reason between the difference between classical and quantum. It is not on a surface level, but it is actually the state of the system and how it predicts. Now, having said the difference between classical and quantum physics, now it is the time that we should start first with what is called the quantization, and who did that quantization and how did it found. Let us find in the next part of our video. So in 1905, Albert Einstein actually took an extra step, and he suggested that quantization was just not a mathematical construct, but that the energy in a beam of light actually occurs in individual particles, which we'll now call as photons, right? So the energy of a single photon of light of frequency f is given by the frequency multiplied by the Planck's constant E equal to hf. So here is the photoelectric effect. As you can see, Einstein explained that the effect of postulating that a beam of light is a stream of electrons or photons. If the beam has a frequency f, then each photon has an energy equals to hf of a single photon. Therefore, the intensity of the beam has no effect, and its frequency determines the maximum energy, and that can be imparted on the particle. So you see, the intensity of beam of no effect, only its frequency determines the maximum energy. That is where classical electromagnetism, which predicts that the electron should be proportional to the intensity of the incident radiation, is not. So to explain this is what the classical electromagnetism. So to explain the threshold effect, Einstein argued that it takes a certain amount of energy called the work function, this one, here you see this one, this is the work function, right, and denoted by psi, and to remove an electron from the metal, that means to dislodge the electron from the metal, right. This amount of energy is different for each metal. If the energy of the photon is actually less than the work function, then it does not carry sufficient energy to remove the electron from the metal. The threshold of the frequency is the frequency of the photon, whose energy is equal to the work function. Well, this is a kind of a first quantization of light, and inadvertently it was Albert Einstein who gave birth to quantum mechanics, right? So this is basically the quantization of light, but this is not all. This is just the quantization, but we need a complete structure of the atom in order to understand and visualize. That is coming up in the next part of our video. So by the dawn of the 20th century, the evidence required a model of the atom with a diffuse cloud of around negatively charged electrons moving around it. Now what we found is that when a gas is heated, it gives off light at a distinct frequency. This is the emission spectrum of hydrogen, and the intensity of the light at different frequencies is also different. I mean to say, by contrast, white light consisting of continuous emission across the whole range of visible frequencies. Now it was in why it is so. Now in 1930, Niels Bohr proposed this new model of atom that include quantized electron orbits. Now you see all these quantizations are coming up, n equals to 1, 2 and 3, and electrons still orbit the nucleus much like a planet orbits around the sun, but they are permitted to inhabit only into certain orbits, not to orbits arbitrarily at distance. So when an atom is emitted or absorbed energy, the electron did not move to a continuous trajectory from one orbit to another, but as it might expected classically, instead the electron jumped instantaneously from one orbit to another, giving off the emitted light in the form of a photon. So as perceived into classical mechanics, that it would continuously move into another phase, but it jumped, and this is basically the differences in energy orbits. The emission spectrum for each element would contain a number of elements. So once it was the closest permitted orbit, it would stay stable forever. Now this was basically Bohr's atomic model, which we have still studied in schools and high-level classes. This was basically another form of quantization, very important concept of fundamental of quantum mechanics. Now the question is that we know that the atoms or the electrons etc. are moving in specific orbits, but the question is that, is this orbit stable, or there are certain movements etc.? What is about the light that and the electrons that are moving in a particle or a wave like matter? Let us look into this gentleman's hypothesis, de Broglie's hypothesis. Now, based on the idea that light and all other electromagnetic radiation may be considered a particle or a wave nature, in 1923, Leo de Broglie suggested the same kind. So what he did is that he actually demonstrated this one, P is equals to h lambda, where he finally the hypothesis came true that all matter exhibit properties of both particles and waves. This is the momentum, this is the wavelength, and this is the Planck's constant. So if we write it in this way, then what we get is that through the double slit experiment, we find that the matter was as wave. A beam of electron can exhibit diffraction just like a beam of light or water wave. Similarly, wave-like phenomena were later showed for atoms or even molecules. So what we find from here is that even if the photons are sent through the slits, one at a time, there is still a wave which creates an interference, right? And neither the classical concept of particle, which was the corpuscular theory of light by Newton, nor of wave can fully describe the behavior of quantum scale objects, either photons or matter. So this was de Broglie's hypothesis. Very important to know that all matter exhibits properties of both particles and waves. But the question is that after that, how it was actually proved. Let us see into the next part of our video. So we are dealing with actually wave particle duality, and this actually concerns about J.J. Thomson, who won the Nobel Prize in Physics for proving electrons are particles, and few years later his son only George Paget Thomson proved in 1937 that electrons are wave. The question is that which one is right? That is a kind of a dilemma. The answer is that both of them are true, and that is why we say that every particular quantum entity may be described as either particle or a wave. And that is why Einstein told that we have two contradictory pictures of reality. Separately, neither of them fully explain the phenomena of light, but together they do. That means you cannot express anything separately. This is a particle or this is a wave. Together we have to take into concern, and we have to answer that whether it is a wave particle duality together. Now we have come to the phase of our video which we have understood the wave particle duality, the birth of quantum mechanics, the matter waves, and everything. Now the question is that this duality of wave and particle creates a lot of concepts which are bizarre and very counterintuitive. One of them is that staying together, and this is what is called, let us see into the next part of our video. Starting from here, when the particles are behaving both in wave and particle manner, what is the next thing that behaves at a duality? And this is what is called superposition. Now there are a lot of concepts and misconceptions about superposition, so I would like to give you a clear clarity on this. Now if you take a kind of an electron, right, then we know that it has got two properties, spin up and spin down. Now let us forget for the time being what is a spin. I will make a separate video because I have to talk a lot about spin, but these are internal properties. Now if the quantum system or any system which has got these two properties, spin up and spin down, are left alone and there is no external interference, neither we are trying to measure, etc., then we call that this spin up and spin down are in a superposition. In other words, we can say that this is in a mixed state of one or more states at one particular time. So it is in a kind of a soup of all possible mixed states, and that is what it is. Remember that when we are not measuring anything, the quantum system is left alone without an external disturbance. This spin up and spin down are in a kind of superposition. Now this actually leads to the famous notion of Schrodinger's cat, when we call that the cat is both alive and dead, and it says that the state of the cat is in a superposition. That means both of the states are alive and dead, as far as the Copenhagen interpretation, which is the most widely accepted interpretation till now in quantum mechanics. So we understood that the quantum system would be in a superposition which is both up and down. You can think of a cat both dead and alive, or a switch on an electric is both on and off, something like that. Now let us see that how we represent those overall quantum states. So we do like this, right? I'm not going into this vertical and this ket and bra. I have made a very detailed video, 3 levels on bra and ket. You can go and check into my playlist in quantum mechanics. However, this is something, let us ignore the numbers for the time being. This is basically we applied over psi, that is the wave function of the system. The question is that on the right hand side, as you can see this icon, what happens when we try to measure them? What happens when we try to observe them? What happens to the electrons when we try to experiment and observe them? So what actually happens, we find either the electron is in state up or in state down. That means the wave function actually collapses. And this is another fundamental concept of quantum physics, which is called the collapse of the wave function. Now when the collapse of the wave function typically happens, what happens is that we can find this in either one state. Either it is spin up or in spin down. But remember, when we are not observing, the quantum system is in a superposition of both up and down. So here the wave function or the wave function of the system reduces to either up or down. And this is how it happens. So we have to remember that when we measure the quantum system, we are going to find the electron in any one state. But before that, we cannot tell which state it would be. So further what we see is that now what are these numbers? The square root of 3 upon 2 and 1/2 is actually directly linked to the probability of finding the system. As we have just discussed that in quantum physics we can only know the probability. So that means that if I square it, now don't ask me why I'm squaring it, I hope you know, and it actually gives the probability of the electron to in the up spin state, and this one if I square it, it is in the down spin state. Okay, so till now what we know is that all quantum information is stored in this wave function, that is this psi, and it is When we are not touching it, it is a superposition, both up and down. And if we try to find it up, we square it, which shows that the probability is this much in the up spin state and this much in the down state. So before measurement, we cannot predict whether it will collapse up or down, but when we measure it, the wave function collapses and we find out into either of the states. This is a clear-cut, a kind of a pseudo-mathematical concept of what is called a superposition. Now, once this superposition has been understood, we can understand that it is in both states. Now, similar to this kind of a Bohr system, when the electron is both up and down, that means that these are somehow related to each other. And what is this relation called? This relation is called an entanglement, or somehow they are entangled with each other. This is another important concept. What is quantum entanglement? Coming up in the next part of our video. Well, first I would like to give you a brief idea about what is quantum entanglement in simple language. So this is what it says, that it is the phenomena that occurs when a group of particles are generated, and in such a way that the quantum state of each particle of the group cannot be described independently. It is written in red, which means that each one of them are entangled with each other. And this is how, if these two particles are, somehow related to each other, even if they are perfectly correlated, and if they're separated billions of light years apart, one particle, if you try to measure, do something, the other particle will come to know. This was a counterintuitive phenomena which happened, and it was these three people, Einstein, Podolsky and Rosen, which is called the famous EPR paradox. They tried to argue and brought upon a kind of a hypothesis which is called the EPR hypothesis. I'm not going to explain right now because otherwise the video is already getting quite long. You can look into what is the EPR paradox. That is a kind of a counter argument which they try to prove that no, they have got something which is called a local effect on that. But anyway, that is a different issue. So what we see is that, say for example, we have two entangled balls, right, and each is in its own box. In this metaphor, the balls can be either yellow or red once observed. For now, for example, it is in a superposition of both yellow and red at the same time. The objects remain connected even over vast distances. That is important, and scientists think of entangled objects really being a single object. But what if one observer decides to look at their ball from a different angle or from one side of the box, right? So here you can see the balls would revert back to a state of the superposition and have a 50% chance of being red and 50% chance of being yellow. Right, so the viewer might find a yellow ball now even though the pair of balls had been previously been red. So as you see here, the observer tries to see it from a different angle, it turns up to 50% red and 50% yellow. Now if the second observer also looks at their ball from the side view or from something else, it will watch that what the first observer saw. So you saw the first observer seeing yellow, it will be yellow. So the answer is that the balls are still entangled, but what the viewer sees actually is basically depending on how they look at the ball. This is the reason that entangled information about the color is not lying within one ball, it exists in the connection between these balls. So this is how what is quantum entanglement explained in a very brief manner, and this is the reason that these three physicists, Clauser, Alan Aspect and Anton Zeilinger, got their Nobel Prize in Physics in 2022, being able to manipulate and manage quantum states. So their intense research and development are actually utilize the special properties of individual particles and to construct quantum computers, which we will look. If you're really interested to know what actually their work are, what is their research, and what is that they prove that two particles behave in a single way, you can go to this video, which contains further details about the Nobel Prize in Physics, a complete journey about their discoveries, their achievements, and a little bit more about quantum entanglement. Right, now we have understood quantum entanglement, we have understood quantum superposition. Now is the question to get into the final and the most important question, that all these things happen but they are still not happening, and that is what is called uncertainty principle, and I will be explaining the uncertainty principle in a different way to clear up the confusion. Well, in general, when we talk of Heisenberg's uncertainty principle, remember that he used this word, which is very difficult for me to pronounce in German. It means inexactness, right? He further used this word, which also means undeterminedness. This is a wrong English, but however, just put to make it understand. Now you see that inexactness refers to the lack of precision or accuracy in measurement or representation, right? It is not same as uncertainty, because uncertainty means it refers to lack of knowledge or information about a particular event, outcome or measurement. So here the first one refers to the lack of precision or accuracy. The second one refers to the lack of knowledge or information, how they can be each other. So it is better to use the original term inexactness or undeterminedness rather than uncertainty principle. However, the uncertainty principle actually shows that there is an absolute limit on the combined accuracy of certain pairs of simultaneous related motions, especially the position and momentum of a particle. So we know that the delta x basically shows the uncertainty in position, and this is uncertainty in momentum, which is greater than or equal to h bar, which is a Planck's constant. We are not worried about that. What I'm trying to make a point is that in case delta x we make it very small because we are multiplying, then we have to make delta p very big because it has to be h bar over 2. Now this actually gives you a kind of a hint that what do we mean by making it small and making the other one big. So in the classical world, we can find out a specific position and we know what exactly the particle is. And in the quantum world, all we get is a probability distribution, which gives us a kind of an answer that the particle might be around here, and this is the width, which is the delta x, which is actually the uncertainty position. However, the position and velocity of an object cannot be measured exactly at the same time. Now, here I would like to object. This is not the right way to represent. What I would like to show you is this one. Uncertainty principle is something which is closely related to what is called a Fourier transform, and I don't want to explain Fourier transform, which is quite complicated and complex. What I would like to show you is this one. Just concentrate on the last line, that it actually shows Fourier transforms of one another, that is position and momentum are conjugate variables. What I'm trying to make a sense is that, let me give you a very quick example. For example, if I get a sound wave which has got a pure tone and which has got a very sharp spike at a single frequency, then if I Fourier transform it through the mathematics, then I will get a kind of a wide shape which has got quite a kind of a long wave and which is delocalized sine wave. Now understand, this is the key point. The wave function for a particle's momentum is the Fourier transform for the particle's position. Now, what do I mean that? I will just show you a quick example. But here you remember that a sharp sound and a spike which has got a narrow kind of a height, it will be expanded into a Fourier transform which is much more longer. So the wave function for a particle's momentum, when we Fourier transform it, it transforms to particle's position. Now what do I mean by that is this. If I get a kind of an original function which is a kind of a pure sine wave and it is a wider function, if I Fourier transform it, I get a kind of a sharp note or a narrower Fourier transform. That means that if I get a kind of a width like this, and if this is the wave function which actually shows the particle's position, and we have just seen that if I Fourier transform any wider function into Fourier transformation, it gets into a narrower function, and this means that a wider function has got a less amount of knowledge because it is quite wide, so the electron can be anywhere, but as soon as that gets Fourier transform, the momentum gets narrow. That means more time that we know about the momentum, we lose out the particle's position. Let me demonstrate in a further example. Here is what we know less about the particle's position. Why? Because the probability distribution is quite wide. So obviously we would know more about the momentum because the Fourier transformation shows that it is narrow. So, and vice versa, the more we know about the position, we know less about the momentum, and that is exactly what Heisenberg's uncertainty principle tells. So you can go into my another video which I have made, misconceptions about quantum physics, which I have just started with uncertainty principle. So this is what it is not about measurement, it's not about intelligence, it is not about the instruments problem, nothing. It actually arises from Fourier transformation. If you Fourier transform the position, you will come to know more about momentum, less about position, and vice versa. Here it is completely demonstrated. You can take a snapshot of this and that would be quite good. So now that we have understood what is the uncertainty principle and how the position and the momentum, once we Fourier transform it, one we come to know one and the less with other. There is one thing which is still left, that another bizarre phenomena where the electron moves in spite of a lesser energy into something which is called quantum tunneling. Now, quantum tunneling is basically a phenomena where a particle is able to penetrate through potential energy barrier that is higher energy than a kinetic energy. This amazing property actually helped us to play some important roles and create something which is called scanning tunneling microscope, or STM. Now let us consider a ball which will roll from this place to another, and if the ball's energy is to overcome the potential energy V, here you see that at the top of the barrier between each valley, then obviously it can roll to the valley of the other, and that is quite, there's nothing problem about this. Is pure classical mechanics, and the ball position will be here. Now here comes something which is very bizarre. It tells that when quantum effects are taken into effect, the ball can tunnel through, it goes through a tunnel through the barrier to the other end of the valley, even if its kinetic energy is less. Now this is quite mathematical. I really don't have the time, and I would make a different kind of a video for that, but just try to understand that even there is a less amount of energy which defies the common sense in classical mechanics, the ball will tunnel through and reach the other end. And this actually helped us a lot, because we have been able to solve many problems. For example, chemical bonds, radioactive decays, and hydrogen nuclei in the sun are actually used to overcome their mutual repulsion in fuse producing sunlight, and that is how it happens. Okay, so we will try to demonstrate this one. So you see, in macroscopic particles such as protons, electrons would behave differently as a consequence of the wave particle duality. Now if I consider a particle with energy E, as you can see, that is confined somewhere with a barrier height of this much, which I can tell as V, and then classically the box will prevent these particles, or this height would prevent the particle from escaping, and it will never reach up to here. It will never reach up to here, right, in kinetic energy. However, if the thickness of the barrier is thin, the particles maybe have a probability of getting through. So the particle won't be able to cross until it gets a very high kick of kinetic energy. This is something which I want to show. So here in quantum mechanics, what it shows that when it reaches a barrier, it cannot overcome a particle's wave function, and it changes, it gets a kind of an equation like this, which is a kind of a, you can understand as a kind of a decay. So what it happens is particularly this, when it reaches a barrier, it cannot overcome, and what happens is that the sinusoidal wave of particles to the barrier goes into exponential decay, and it exits the barrier and gets transmitted to the other end with a kind of a smaller amplitude. Smaller amplitude in the sense, I need to show the mathematical part, but it is not the right time. So this is the concept of quantum tunneling. It even goes because the exponential decay happens and it exits the barrier, this blue zone, which shows that equation, into a sinusoidal wave with a smaller amplitude. Now with all this understanding of quantum tunneling, superposition, etc., can we make a better device which will be faster, easier, and proves a better calculation? Coming up in the next part of our video, we will just quickly look into what is quantum computing, the basic concept. Well, if you see, in case of a classical computer, which we generally see about, the information is stored in bits and bytes, and all this information, the Facebook, Instagram, YouTube, whatever we are saying, it is stored in fundamentally in bits and bytes, that is 0 and 1. So each of these has got certain hexadecimal codes, A, B, C, and so we all know this, and it goes into kilobyte, megabyte, terabyte, and petabytes. The question is that here we are taking place in 2 bits, that is only 2 possible states. But quantum mechanics, as we know, it takes what is called qubits. That means quantum bits. And this is what it happens. The value depends on the superposition of 0 and 1. So you see that once a quantum system is left alone, it will be either in spin up or spin down. Exactly, it happens like that. And it can be in both the states, and it is a coherent superposition. Now the question is that can we use the superposition in order to do a better computation? Now I would like to demonstrate this. See, rotating coin is always in a superposition head and tail, right? And when it falls, we get either it stops in a head or a tail. So that means we are behaving in type of bits, right? Either 0 or 1. Now the thing is that this is a classical bit and quantum bit, and you see the difference. This is either empty 0 or 1, and it is 1/3 of 0 and 2/3 of 1. Here it is 20 reds beads and 20 blue beads. It tells that 820 of 0 and 120, and further on and further on. So here what I am trying to make a point is this superposition gives the ability of a quantum system to be in multiple states at the same time and measure it. Obviously, if it opens all the doors at one time, obviously you can locate where your friend is standing. Let's take a quick example. So quantum superposition is, as we have seen, a fundamental principle of quantum mechanics. If we take classical mechanics as itself, here the things are well defined. The nature of the system is guided by deterministic mode, and the outcome is either 0 or 1. That means we are going from one place to another. In a quantum state, what we have seen is that this is basically a kind of an AND. That means the quantum state can be both 0 as well as 1. And this is the classical state, right? Either 0 or 1. So this is the difference between quantum state when we get superposition of particles between 0 and 1, and this is 0 or 1. We can tell that the cat is dead and alive. That means simultaneously alive and dead, and this is very useful for quantum computers. I will show you a simple analogy. This is classical computer. When we try to calculate, we get the combinations either 00, 01, 10 or 11. And we will process one data at a time. When we use quantum superposition, this actually has multiple phases. For example, it has 00, it has got 01, 10 and 11. That means it will process all the data at a time. So the number of options doesn't really increase. It is the same 00, 01, 10, 11, both for classical and quantum computer, but it processes the data all at a time. That means these are the number of combinations. If I take 3, you see 1, 2, 3, 4, 5, 6, 7, 8. That means it processes 8 quantum system at a time, and that increases the speed. If you further take this one, and you see this is the total number of, if I take 4 qubits, then how you see that quantum computer processes all these 16 states which you can count out simultaneously. So the superposition, which actually opens up a door in a faster, much faster and a better computer processing. So 2 to the power 64 qubits, it gives this amount of possibilities, and you understand that this amount of possibilities, when it is opening all at a time, how fast it would be. So it would be 1 million terabytes. So a 2 gigahertz general laptop or a computer will take 400 years to compute, and 2 to the power 53 qubits will have this many amount of possibilities. So the current Google's Sycamore, which it demands, will process the data in 3 minutes 20 seconds, and the IBM supercomputer, which was a debate by it would take 10,000 years to complete, and this was actually told by Einstein as a spooky action at a distance. That means how can 2 quantum electrons stay at the same state at one particular time. Anyway, Einstein's spooky action of distance is no more spooky. It is now being used by Sycamore as well as by IBM. So it would be very fast, and we have finally proved quantum computing is possible, although there are a lot of ifs and buts, and we have understood how quantum mechanics can be used for the betterment of service. If you want to know a little bit more about this particular quantum computing, I have a very detailed video on this. You can go and check out all about quantum computing in my playlist. Well, that's all. I know the video has been quite long, but I just thought to give you a complete understanding about all the fundamental concepts. Most importantly, remove the misconception. So this is the summary. What is quanta? First solve a conference. We understood the birth of quantum physics. We now understood what is the actual difference between classical and quantum physics, photoelectric, this quantum, and most importantly, the uncertainty principle, which we have understood comes from something not due to errors or anything, but from Fourier transforms. Thank Thank you very much for watching this video. If you have liked this video, please press up a thumbs up and click on the bell icon, and do subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students. I'm available for any kind of a clarification at this email ID. You can also subscribe to my channel exclusive to Einstein General Relativity, and you can follow me on my Instagram, Facebook and LinkedIn pages. Thank you for watching this video. I will be waiting for your comment how you like this video. Physics for Students will be soon back with yet another very interesting videos on physics, mathematics, and we will continue our learning. Till then, goodbye.